Hi, I just wanted to go over the problem that I showed you the other day in class via video, but there were requests for extra help on an extra clarification. So what you should have seen, from what I understand, everybody understood this rule of thumb, and what you should have seen from the rule of thumb model is that it sucked. The goal is that we want to use a better evidence-based model to model the temperature decrease in a dead body over time. So the method we're going to apply is something called Newton's law of cooling. Newton's law of cooling is what we call a physics-based or mechanistic model. It's not a line like we just saw in the rule of thumb. So how it works is we have T of t is the temperature at the tth hour. So for example, if I plugged in t equals 1, that would represent the temperature of the dead body at 1 hour after death. T at 2 would represent the temperature of the body 2 hours after death, and so on. Now this model works for everything that cools, not just a dead body. For example, it could be a metal rod that you heated up and laid on a table. The temperature of that metal rod as it decreases would also follow Newton's law of cooling. Or it could be the temperature of a cup of coffee that you poured out and placed on the table. What distinguishes each application that you use this model, it's a very powerful model since it works for all these different applications, is the value of the parameters C, R, and K. Just like a line, if you have a line, the formula for a line is y equals mx plus b, the m and the b are considered parameters. So all lines follow this formula, but once I know the exact value of m and b, I have one specific set line and I can plot that line. So the math notation that might have tripped you up, that's the really good stuff that we have to understand, is we have this formula, T of t is equal to C e to the minus RT plus K. The little t represents the hour after death, and the capital T represents the temperature T hours after death. E is a number. It should be 2.718281. It's a special number, and it's named for a mathematician named Euler. The E in Euler was where the little e came from. So to make a formula, the goal is to make a formula so that I can actually make a table like the rule of thumb and get the y values when I plug in the x values of t. So I need to get rid of this capital C and the little r and the capital K. How do I do that? Well, I fit the parameters to data and logic. So for example, logic tells me that this first term will actually damp out to 0 as t gets large. So this first term will go away when I have larger and larger values of t. So for a huge time, the formula will be approximately 0 plus k. Well, that means as far as I go out in time, that eventually whatever the dead body what I would think it should be, like 10 days from now, will be the value of k. So k is the number the temperature tends to as time goes on. As you probably have thought about in class, if a dead body was laying in a room, you'd expect after 10 days that this dead body would be exactly room temperature. So I can set k to be the room temperature, which is approximately 70 degrees Fahrenheit if we're not in our room in Richardson Hall. So that I'm going to replace that k with 70. So one of those letters has disappeared. I also know that at time equals 0, a good guess is that the human body was around normal temperature, which is 98.6 degrees Fahrenheit. So if I plug in the x value of t equals 0 into the formula, I should get the y value of 98.6. So I'm going to plug in t equals 0 into the formula, and I know that that should be equal to 98.6. Now e to the 0 is 1. Anything to the 0 is 1 other than 0 to the 0. So I'm going to replace that e to the minus 0, I'm going to replace it with 1. So here I am now. I have this equation. C times 1 plus 70 is 98.6. And now I can solve for C. This is a simple algebra formula which you saw in the Red Hawk Learning Center. So solving for C by subtracting 70 from both sides will give me C equals 28.6. So this is what my formula looks like now. I have one more letter to get rid of, and that's R. How do I do this? Well, I need the seventh law of exponent. The opposite or the inverse of the e function is something called natural log x, ln x. There's a button on your calculator that's called ln x. It is the inverse of e to the x, so it undoes e to the x. Here you see the rule, natural log e to the x is x, and e to the natural log x is x. They're opposites of each other. I also need another data point to apply this to get rid of this r, and I'll use an actual data from a paper of an actual body that cooled after death. From number 4 on your in-class assignment, which I posted on Canvas, we have at time equals 3 hours, T of T was 96.5 for that particular body, and I'm going to use that data point. So I'm going to plug in T equals 3 here for T, and I'm going to set that thing equal to the y value at T equals 3, which is 96.5. This is very similar to the T equals 0. So that's where I'm at now, and now I can subtract the 70 from both sides. And that gives me 28.6. E to the minus r times 3 is equal to 26.5. Now I'm going to try to get at this r up here. So I'm going to divide both sides by the 28.6. And I get e to the minus 3 times r is equal to 26.5 divided by 28.6, which is approximately 0.93. Now, if you don't go in this order and you try to get rid of, for example, the ln by ln here, it will be incorrect. You need to go in exactly this order because you're undoing the order of operations. So you have to go back in that same strict order. So here I am now at e to the minus 3r is equal to 0.93, and now I'm going to natural log both sides. So I natural log the left and I natural log the right. Now natural log and e are inverses of each other, so they cancel, and I put that in quotes because it's not quite what we mean by cancel normally, but they cancel each other out. And I'm left with only the exponent, minus 3r, is approximately equal to minus 0.76. Now this natural log 0.93 I calculated straight off the calculator, which you have a button on your calculator as well. Now to get at r, I just divide both sides by minus 3, and r is approximately minus 0.025. So that's my formula. I have now c, which is 28.6, r, which is minus 0.025, and k, which was 70. So how do I test my formula? I think this might be where you were confused. I have the formula. How do I test it? This was number 4's data table of an actual body. So I'm going to now crank out what happens when I plug in the formula. So I take the x value of t equals 0, and I plug it into the formula for t equals 0. So I put in t equals 0 here, and 0 times anything is 0, so that goes away. And I get the y value of 98.6, close to 98.9. I do the same thing with t equals 3. If I take t equals 3 and plug it in for t, that's all I did. I plugged it in for the formula. I get 96.5. Not bad. They're a perfect match. Now I take 6 and plug it in for t into the formula. After I punch it out on a calculator, I get 94.6. And then I do the same thing for t equals 9. And you see that looking at them at t equals 9, they're a perfect match. Almost perfectly every time. 94.5 is pretty close to 94.6. So this model is doing really well on number 4. What I'd like you to do is go through the same steps using the table in number 5. Try it again for number 5. You may have a little trouble entering it into the calculator correctly, and I remember that from last semester. If you do have that trouble, go back to my work and see if you can recreate the same numbers using your calculator. If you can't, screenshot your calculator or take a picture of your calculator and send me what you're typing. Or you can send me an email or a text saying, I'm typing in this order and this is what I'm typing in my calculator and I'm not getting the same answers as you. So this particular problem will be on the quiz Please call me or text me if you have any trouble.